Single planetary gear sets operate under certain laws, 5 in all, to achieve various drives on vehicles. Let's review the 5 laws that govern these drives. First, there's neutral, governed by law number 1. When there is an input and an output, but no reactionary, the result is neutral. Next is law number 2. When the planet carrier is the output and there is a reactionary, we get gear reduction. This sets our vehicle in motion. After this comes law number 3. When the planet carrier is the input, the result is overdrive. Then there's law number 4. When the planet carrier is the reactionary, we get reverse. And finally, law number 5. When any 2 members are locked together, the result is direct drive. But for the mobility required today, many vehicles must have more speeds and capabilities at their disposal. One way to get this required mobility is by changing the relative sizes of gear members in a set. To widen the selection of ratios still more, we can use 2 or more sets in combination. Such combinations, called multiple planetary gear sets, are typical of certain transmissions. To demonstrate how connecting the sets multiplies ratios, let's use just 2 sets first. We'll put both sets in reduction. One set has a ratio of 3 to 1, and the other a ratio of 4 to 1. Therefore, we get a total reduction of 12 to 1. This is the lowest speed. Now, by putting the small gear set in direct drive and keeping the large one in reduction, we get a total reduction of 4 to 1. This is second speed. By putting the small set in reduction and the large one in direct drive, we get a 3 to 1 reduction, or third speed. With both sets of gears placed in direct drive, we get a ratio of 1 to 1, with no gear reduction. That's fine for forward, but vehicles have to back up, too. How do we get reverse? Well, to our 2 sets, we could hook up a simple reverse set. With the planet carrier made reactionary by a band, this would give us reverse. We could also transmit forward through the simple reverse set by putting it in direct drive. Actually, such a reverse would be too bulky. Space and weight can be saved by using what is called a compound reverse, which you'll come across in certain truck transmissions. With our compound reverse model, let's keep in mind that this is our front set, this is the intermediate set, and this the reverse unit. To see how this works, let's build up the compound reverse unit step by step. The ring gear of the intermediate set is connected by this shaft to the sun gear of the reverse unit. This connecting shaft is hollow to allow the output shaft to pass through it and connect the planet carrier of the intermediate set to the planet carrier of the reverse unit. We have the planet carriers of these two units connected by the output shaft. And we have the ring gear of the intermediate set connected to the sun gear of the reverse unit. The next thing we add to the reverse unit is its ring gear, which can be held reactionary by a cone-type clutch. Now let's follow the flow of power in this compound reverse setup. The sun gear is the input in the intermediate set. The load on the output shaft, which connects to the intermediate planet carrier, makes it the reactionary. With this planet carrier reactionary, the intermediate ring gear will move in a direction opposite to that of the sun gear, which is driving. This gives us the reverse movement we want. This reverse movement of the intermediate ring gear is transmitted by this connecting shaft to the sun gear of the reverse unit. By making the ring gear of the reverse unit reactionary, the planet carrier becomes the output and follows the direction of the sun gear, which is driving. The reverse planet carrier transmits the reverse through the output shaft to the wheels. That's pretty complicated, so let's look at it again, remembering that the reverse actually takes place in the intermediate set, with the input the sun gear. The planet carrier, controlled by the load on the output shaft, causes the ring gear to turn in a reverse direction. The ring gear transmits this movement to the reverse unit's sun gear. Locking the ring gear in the reverse unit gives the reverse planet carrier, which is now the output, no other course but to follow the sun gear's reverse direction. Thus, the output shaft and the wheels also turn in reverse, and our vehicle backs up. We can also go forward by releasing the reverse unit from the hookup. We place the intermediate set in reduction and keep the front set in reduction. The flow of power is then allowed to pass right through the reverse unit, which is now just going along for the ride, as it does in all forward speeds. Talk about going along for the ride. In this truck, the driver might be doing just that, because the combination of planetary gears and hydraulic controls does most of his work for him. We can get even greater variations in output ratios by adding another source of power to the planetary gear setup, giving us two inputs. One input is used to drive one of the gear members, the ring gear in this case. This input is run at a fixed speed. The other input is hooked up to the sun gear, and its speed can be varied. First, let's rotate the sun gear in the same direction as the ring gear, which maintains its fixed speed. By the use of indicators, we will see the various speeds. The first indicator is connected to the ring gear. The speed of the ring gear will not change. The second indicator is connected to the sun gear. The sun gear speed can be varied. The third indicator is connected to the output. Now let's increase the speed of the sun gear. This results in variation of the output speed. The faster we drive the sun gear in the same direction as that of the ring gear, the greater will be the output speed. The output speed always stays between the two input speeds. No matter how we vary the sun gear speed, the output always stays between the two input speeds. Now let's see what takes place when we rotate the sun gear counter to the ring gear's direction. We'll keep the ring gear speed constant and vary the sun gear speed. The direction of the member with the faster tooth speed, that means the greater number of teeth passing a given point, is the direction that the planet pinions will follow. Consequently, that's the direction the output shaft will take. Increasing the counter rotation of the sun gear slows down the output speed. When both input tooth speeds are equal, the output shaft stops. By increasing the speed of the sun gear still further, its tooth speed goes beyond that of the constant input and pulls the planet carrier with it, causing the output shaft to reverse its direction. We can see that giving planetary gear sets two inputs instead of one widens their possibilities, making them especially useful in driving tanks. For instance, this tank uses the two-input principle on its two planetary gear sets, one for each track. A mechanism called the differential controls the speeds of the second inputs and facilitates steering by transferring power from one track to the other. In this way, the steering differential permits one output to be speeded up while the output on the other track is retarded. We can even make the tracks go in opposite directions and give us a pivot turn, like this tank about facing in its own length. Look how easy and effortless driving can be with hydraulically controlled planetary gear sets. Just a slight push of the wobble stick to the right, and 50 tons of steel obediently turn in that direction. Any movement of the wobble stick gets a response from the tank because it hydraulically controls clutches and bands inside the transmission, with practically no more effort than was used to apply the clutches and bands on the model. No matter how complicated the hookup of the actual planetary gear sets may appear, just remember that basically it's only a number of simple sets arranged together. So if you understand simple planetary gears and know the 5 rules that govern them, multiple planetary gear sets should give you no trouble.